2023 question number 2. This is a really great question. It's a bit of a long one, but it's very, very interesting. So we have this bit about Linus Pauling and electronegativity, and then it says you've got this equation which gives you the electronegativity difference between atom A and atom B, and it says calculate the difference between chlorine and hydrogen, and then it gives you all the data to just basically put into this equation. So this, for a very simple 1 mark, is basically just plugging numbers in. So I'm going to go ahead and plug those numbers in up here. So I've got this chi Cl minus chi H is equal to 0.102, and then I've got the square root of the bond dissociation energy of HCl, which I'm given as 427, minus hydrogen 432, plus chlorine 244, so the average of the two. So it's the difference between HCl and then the average of H2 and Cl2. And I basically just go ahead and I calculate that whole thing, which I'm not going to bore you with. And out it comes 0.962, 0.962. So to be honest, if you can't do this on your calculator, then there's not much I can do to help you, I'm afraid. So question B. As this gives the difference, it is necessary to choose a reference point in order to gain values for individual elements. Pauling originally chose hydrogen with 2.2, and then using this and your knowledge of trends in electronegativity, I'm not really sure, I guess they just mean, do you know which is more electronegative, hydrogen or chlorine? Hopefully you do. So then calculate the electronegativity difference for chlorine. So if I know that hydrogen is 2.2 and I know the difference is 0.96, then obviously chlorine is going to be 2.2 plus 0.96. Okay, so 2.2 plus 0.96 gives me 3.16. Another very generous mark there. So other scientists use different ways of calculating it. So we have this Mulliken value, where it takes it from ionization energies and electronefficiencies, and it says calculate the Mulliken electronegativity for nitrogen. Okay, so let's go ahead and do that. So we're going to have, I can just about fit it on, electronegativity for nitrogen is 0.00197 multiplied by this number plus this number. But very trickily, they're giving you this in kilojoules per mole, they're giving you this in electron volts. But they do very kindly give you the conversion. So this is just going to be 14.5 multiplied by 96.49, because if 1 electron volt is this many kilojoules per mole and I've got 14.5, I just multiply them together. So let's do that. Where I have EI, I'm just going to have 14.5 multiplied by 96.49 plus 6.8. and then plus this 0.19 on the end. Okay, and again, it is just a simple case of plugging those numbers into your calculator. And you get 2.96. Okay, so far so good. 3 easy marks for just doing simple calculations. Now this is where the question starts to get a little bit more interesting. So we have the Van Arkel or Van Arkel-Ketelaar triangle here, ionic metallic covalent, and we are given some electronegativity values, and then we have the positions of several different sort of binary compounds on here. Now the important thing to understand here is, and it does tell you this here, it has the average and the difference. So this axis is my average electronegativity, and this axis is my difference in electronegativity. Okay, so some interesting things to note about this. So if the difference is on this axis, then anything that's a elemental elemental molecular substance like H2 or F2 or Cl2, that would obviously be somewhere along here, because the difference between Cl and Cl is 0. Okay, and then the higher the average electronegativity, the more covalent it's going to be, because something like F2. So F2 would be right up here, because there's no difference, so we're down at 0, and the average electronegativity of 2 fluorines is going to be very, very high. Okay, so that's how this works. And then it says identify the letter in the answer booklet which represents the position of the following substances. So all I need to do is just take this data, apply it to these, and find it on here. Now, I tried to think about different ways that you could do this. For me, the simplest way is just to calculate one of these values and see if you can find it on the plot. I guess you could sort of think about, okay, well, try and find this aluminium phosphide. Is it metallic ionic covalence? Look on the diagram. But I think it's just easier if we go ahead and calculate the average of each one. So aluminium and phosphorus. I'm just going to do 1.61 plus 2.19 divided by 2. I get 1.9. So then I look on here for 1.9. Here's 1, here's 1.5, here's 1.9, so it's I. Okay, so that's going to be I. Then number 2, CSH. So CS is 0.79 plus hydrogen is 2.2. Divide that by 2, and I get 1.495. So I go along here. 1.495 is basically 1.5, and I've got E. It's easy to get confused here and go for A. A would be 1.45 rather than 1.495. You can double check it by then just calculating the difference between the two. So if I calculate the difference between cesium and hydrogen, I'm going to get 2.2 minus 0.79, which is going to give me 1.4. And you'll see that E comes out about 1.4. So that's E. BRF, well, BR and F is going to be 4 and 3. Okay, so it's going to be 3.5. Can I do it without doing it? By which I mean, can I do it without doing the calculation? So if fluorine is 4 and bromine is 3, the average is going to be 3.5. And you see there's only one that's got the average of 3.5. So that's L. All right, and it's obviously, BRF is like BR2 or F2. It's very, very covalent. And the difference is going to be about 1. So that works out. HGO. So 2 and 3.44, 2 plus 3.44 divided by 2 gives me 2.7. So 2.7 brings me out. I've got an option here of G or K. 2.72 is probably going to be G. I'm going to double check by working out the difference and hope the difference is going to be about 1.45. So if I do... Actually, I don't even need to bother. I can just see 3.44 minus 2 is 1.44. So that is G. And then SiC. So Si 1.9, carbon 2.55. 2.55 plus 1.9 divided by 2 gives me 2.225. So 2.225. So it's going to be along here. It's probably going to be J. Double check with the difference. The difference is going to be about 0.65. So yeah, that gives me J. Okay, so nice and straightforward. Just put those all in. Just going to be I, E, L, G, J. And then identify which of the 5 substances in part D displays the greatest degree of metallic character in its bonding. Don't forget you were told metallic is all the way down here. So just look for the one that's sort of furthest into this corner here. And what did I have? I had I, E, L, G, and J. So you would go with I down here. Does that make sense in terms of what the constituent elements are? I mean, it's obviously not going to be BRF, it's very covalent. And then these other ones are all sort of, it's a bit hand wavy really. Just go for the one that's furthest down in the corner. Okay, so we're going to go with ALP. Okay, excellent. That was also fairly straightforward. And now the next question, I think, is a really nice question. So we have 3 substances. cesium bromide and carbon monoxide have been marked onto another Van Arkel-Ketelaar plot. Based on your knowledge of trends, try and identify which point it is. So CSCl, okay, NAK and GAN. So I need to find which of these, A through K or L or whatever it is, corresponds to each of these, but I'm given 3 points. So the way it works is, obviously, one of these starred ones corresponds to something that's similar to one of these, and I can work it out from that. And it really does, like, it's very nice the way they question it, the way they structure it. It sort of holds your hand the way through it. So, if I start with CSCl, which of these three am I going to use to work out where CSCl is? Obviously, CSBr, because to go from CSBr to CSCl, I'm just replacing the bromine with a chlorine. Now what that's going to do, because chlorine is more electronegative than bromine, by a little bit, okay, it's going to raise the average electronegativity. So from here, I'm going to want to go a little bit to the right, because chlorine is going to bring that average up. And because CS stays the same, if I increase the electronegativity of the other element, the difference between them is also going to increase. So it's also going to go a little bit up as well. Okay, so I want something that's a little bit to the right and a little bit up ahead. Okay, which is obviously going to be B. All right, it's not going to be A. A is going to be really, really ionic. All right, so I think we're safe to just go with B for that one. Nice and easy. Now, they try and make it a little bit more difficult. So, this alloy of sodium and potassium, that's two metals. Okay, so I'm going to compare that with cesium, which is just the pure metal by itself. It's useful to just refer to the periodic table here. So I've got cesium down here at the bottom of group 1, and I'm replacing it with a mixture of sodium and potassium. So sodium and potassium are both going to have, and this now comes back, you can see cesium is right down on the bottom axis because there's no difference in electronegativity. And I'm going to have to choose between N, N and O. Now, sodium and potassium are different elements, which means that the difference in electronegativity cannot be 0. So I can eliminate O. Okay? And then the average. So as I go up group 1, my electronegativity value is going to increase. So if I compare the average electronegativity of this compared to this, I should expect my average electronegativity to increase. So I've got two options, M and N. They've both got a tiny difference because sodium and potassium are different. N, the average electronegativity is slightly higher. M, the average electronegativity is slightly lower. So my answer is N. So that is N. And then the hard one. So I've got carbon monoxide, and I need to find this gallium nitrogen thing that I've got here. Okay, so if we look on the periodic table, I've got carbon monoxide, carbon and oxygen, and I'm replacing it with gallium and nitrogen. Now, this is a little bit hand-wavy. And rather than sort of try and work out some more robust way of doing it, I'm going to try and walk you through how I did it. So, I thought to myself, well, if I've got carbon monoxide, that's the average of those two is going to be about the same as the average of nitrogen. Okay, so the value on here, I think nitrogen, N2, is going to be about there. Okay, and then I'm in nitrogen is NN. I'm replacing one of the N's with gallium. What's that going to do to my average electronegativity? Well, if my average for nitrogen is here, gallium is obviously less electronegative. So it means that my gallium nitrogen compound is going to be to the left of carbon monoxide, which is great because now I can just ignore all of these. Probably not going to do that one, probably not going to do that one. I'm looking at E, I, maybe P, Probably not though, because I expect them to be much, much closer. Okay, so I'm looking at E and I. Is the difference in electronegativity going to increase or decrease? Well, carbon and oxygen are very close together. So the difference isn't going to be much, all right? And it's about 0.9. Then you just have to decide, well, do I think the difference in electronegativity between gallium and nitrogen is bigger or smaller than the difference between carbon and oxygen? Now, these are in the same row, the same period. It's 2 elements across. Nitrogen to gallium, it's 2 periods down, 2 groups across. So there's going to be a much bigger electronegativity difference between gallium and nitrogen. So that means it's going to have to be going up. So to the left of carbon monoxide and above carbon monoxide gives me E. Okay, hopefully that makes sense. You know, that's easy enough to follow for you. All right, so I get B, N, E are my answers. Maybe if you've got a better way of working through it, you can let me know, but that's what I got. Okay, and then boron nitride, and we're asked to work out chemical equations, which we were also asked to work out in the first question this year. So they've been very generous asking us to work out these equations. So boron nitride can be formed by boric acid, H3BO3, and ammonia, NH3, to give me Bn. Obviously there's another product you can do by inspection. You can just see, well, I've got boron, I've got nitrogen, I'm left with hydrogen and oxygen, so the other product is going to be water. And that makes sense because this is boric acid and ammonia is a base, so this is just a neutralization reaction. And a neutralization reaction you should expect to make water. And then I just go ahead and balance it. I've got my boron, I've got my nitrogen, and then I've got 6 hydrogens and 3 oxygens, which is 3 waters. Easy enough. Okay. Second one, slightly more difficult. So now I've got B2O3 plus N2, I'm reading this off here, boron trioxide, nitrogen, and calcium hexaboride, plus CaB6, which produces Bn, and calcium oxide as a byproduct. And I don't need to add in anything else because I've got my borons, I've got my oxygens, I've got my nitrogens, and I've got my calcium. Okay, so then you just need to balance it. Okay, and you can balance it however you like. The easiest way to do this is because I've got boron in both of these, so that's going to be a little bit tricky to balance that first. So I'm going to balance this first. So I've got 1 calcium, that's fine. 3 oxygens, so I need to have 3 of these. And now I've got 3 calciums, so I need 3 of these. And now I can leave the nitrogen, because it's elemental, I just leave that to the last, right? Because whatever I get for all the others, I can just add in the coefficient for that. So then let's do the borons. So I've got 3 6s is 18, plus 2 is 20. So I'm going to put a 20 there. And now you can see I've got 20 nitrogens, so I've got 10 of O's. And we're done. And now the question quite nicely pivots to a unit cell question, which is always a very welcome entry into the situation. So we have several crystalline forms. We've got the C form, the H form, and the W form. And you're given the picture of each one. Sorry, I should have printed this in colour. It's a little bit more difficult to see. You can just go online, you can see the colours, but we'll try and work it out still. And you're given parameters, so dimensions of all of these crystals, and then you're asked to work out a volume, a density, and a number of atoms. Okay, which is quite nice because essentially these 2 questions are the same as these 2 questions, but just with a slightly different shape. So calculate the volume of the CBN unit cell in centimetres cubed. So here it is. It's a cube, and it's 3.63 angstroms. Now, you should really have practice doing this, because this question is just all about the unit conversion, because hopefully you can all multiply this number, so you can all cube this number. All right. The only thing you need to do is, because it tells you to do it in centimeters cubed, you've got to convert your angstroms into centimeters. So, how would I do that? I'm a little bit prone to making mistakes. So, what I do is I go 3.63 angstroms. It does tell you to use the formula page here, and the formula page does very helpfully tell you the unit conversion. Okay, so I would write 3.63 angstroms is 3.63 times 10 to the minus 10 meters, which is not helpful because I want it in centimeters. Now I know that 1 meter equals 100 centimeters. Got to work through every stage just in case I make a mistake. So I know that this many meters is going to have 100 times more centimeters. Now, this is where it's really easy to make a mistake. And if you're really unsure, I would get your calculator out, because it's so easy, anybody can do it. They see this number and they want 100 times more and they make it minus 12. But obviously, because it's minus 10, 100 times bigger, it's going to become minus 8. So this is going to be 3.63 times 10 to the minus 8 centimeters. You know, and if you're really not sure or think you might make a mistake, just double check on your calculator, just really quickly. That is that, times it by 100, gives you, well, I'm not going to do it, but you can count them all out for you, and you get minus 8. Okay, and then the volume is just 3.63 times 10 to the minus 8 cubed. Okay, so I'm just going to cube that value, and I get 4.78 times 10 to the minus 23 centimeters cubed. Lovely. Then it says calculate the density in grams per centimeter cubed. So I've got the volume, now I need to know the mass. So what mass of Bn is there inside here? Now the strategy for this, so let's just make sure we're doing this carefully. So my density is going to be my mass divided by my volume. Now the strategy is I need to work out the mass that I have inside this unit cell. So the first thing I do, number one, is I find the number of atoms. Okay, and then two, I convert grams per mole to grams. Okay, so how many atoms of boron are inside this unit cell? Well, on the corners, I've got 1, 2, 3, 4, 5, 6, 7, 8. And each corner one has got 1/8 of a boron atom inside the unit cell. Okay, so the things here to remember are, if you're inside the unit cell, that's the whole atom. If you're on the face, that's half an atom, because the face will sort of cut down the middle of the atom. If you're on an edge, you know, if you're on the edge of the unit cell, that's a quarter, and if you're on the corner, that's an eighth. Okay, and you can spend some time by yourself working out those if you're not 100% sure how to visualize them. So I've got 8 on the corners, and each one on the corner is 1/8. So let's just tally it up here. I've got 8 times 1/8, plus I've also got 1, 2, 3, 4, 5, 6 on the faces. And it should be clear that those are all on the faces. This is the top face, the left-hand face, the bottom face, this is the front face, that's the back face, and that's the right face. And a face one is a half. So it's 8 times 1/8 plus 3 times a half. Okay, that's 1, and what am I talking about? 3 times a half. How did I get 3? I've got 1, 2, 3, 4, 5, 6. 6 times a half. 6 times a half. 6 times a half is 3. Okay, sorry if I caused confusion there. So my corners, my faces, 8 times 1/8 is 1. 6 times 1/2 is 3. Gives me 4. Now, at this point, hopefully, you can start to think a little bit more carefully. Now, I know it's difficult when you're doing the test to sort of spend time actually thinking about whether your answer makes sense, but it should be clear that in a moment, I'm going to do the same process for nitrogen. Nitrogen must come out as 4. If you don't get 4, you've done it wrong. And the reason you know it must be 4 is because this is all Bn. So I know that the empirical formula is 1 boron to 1 nitrogen. So if I don't get 4 for nitrogen, I've messed it up somewhere. So I can now look, and this is where the printing and this gets a little bit tricky. These 4 nitrogen atoms, it should be clear, hopefully, fingers crossed, that you can see that those are all within the unit cell. Okay, none of these are on the faces. Like, so this bond goes down, this bond goes down, this bond comes to the right, so that means that's inside the unit cell. And it's happening all over, okay, so I'm going in, that's inside the unit cell. I'm going back from this one, I'm going back from this one, so that's inside the unit cell. Here, this is on the bottom face, I go up, I'm inside. This is on the corner, I go up, I'm inside. So all 4 of these are inside. So I don't really, it's like if you want to do the calculation, it's 4 times 1 equals 4. So that's great. Okay. So then what I do is I work out the mass of each of these. So I do 4 times boron, which is 10.81, plus 4 times nitrogen, which is 14.01. Okay, and I'm going to work that out because it's going to be a little bit easier. 10.81 plus 4 times 14.01 gives me 99.28 grams per mole. But you'll remember, to work out the density, I need to know the mass. So this is the thing that always trips people up, is how do I convert the grams per mole into grams? Well, if this is for 1 mole, all right, 1 mole is a lot, yeah, I'm going to divide it by how many there are. So it's going to be, the mass is going to be 99.28 divided by Avogadro's number. Now that's a calculation that it takes students a long time to sort of, it's a very simple calculation, but the sort of logic behind it can take a little while. So it's worth having a think about it if you're not 100% okay with that. So I'm going to divide that by 6.02 times 10 to the 23. It's going to be 1.65 times 10 to the minus 22. And then I can just do my density calculation. So now my density is my mass, 1.65 times 10 to the minus 22, divided by the volume, which I found up here, 4.78. 0.78 times 10 to the minus 23. So divide that by 4.78 times 10 to the minus 23. Gives me 3.45 grams per centimetre cubed. Outstanding. I always say to my students, just think about this number. Okay, you know that one centimetre cubed of water equals 1 gram. That's the sort of magnitude of value we're looking at. Okay, so if you were to have the density of a gas, you'd expect it to be less than that. If it was a metal, you know, I don't know what the values are. Like if you have 1 centimetre cubed of copper. Okay, imagine I hand you a 1 centimetre cubed of copper. What's it going to be? It's going to be about 5 or something like that. 5 grams in that centimetre cubed. Because it's really easy, because of all these powers and all the unit conversions, for you to get some crazy answer here. So if your answer here is sort of 3.45 times 10 to the minus 8, obviously not, right? There's just absolutely no way that it can be that density. Likewise, if you've got 3.45 times 10 to the power of 18 grams per centimetre cubed, now I'm not a physicist, but that's probably sort of like the density of the centre of a star or something stupid, okay? So just think, does this answer make sense? Yes, that is the kind of number I'm looking for, all right? Now, number 3, calculate the volume. Basically now you just do the same process, but instead of this one, it's this one, okay? So I need to work out the volume of this. I'm told that this is 1.47 angstroms, and I'm told that this is 6.66 angstroms. Now, I do remember when we did this paper back in 2023, a lot of students spent a lot of some time working out how to calculate the volume of a this hexagon prism thing, okay? But if they just looked carefully, very kindly, they were told how to work out the area of a hexagon, all right? And then you just multiply it by the length. Okay, so I'm just going to go ahead and do that. So the volume is 3 root 3 over 2 multiplied by the side length, and the side length is 1.47. Okay, so it's 3 root 3 over 2 times 1.47, but I've got angstroms. And you'll remember I did this conversion up here, so angstrom into meters into centimeters. So I can just go ahead and do that times by 10 to the minus 8. Okay, so that's the volume. No, not at all. That's not the volume. Oh, it's the area. But I can just, if I write volume, and then I multiply it by, so what I've worked out there is the area of the hexagon at the bottom, and I'm going to multiply it by the length of the prism to give me my volume. So I multiply it by 6.66 times 10 to the minus 8. Okay, so 1.47 times 10 to the minus 8 multiplied by 6.66 times 10 to the minus 8 divided by 3 divided by root 3 divided by 2 gives me 2.54 times 10 to the minus 15, which is not the correct answer. So what have I done wrong? So this is side length squared. Alright, so let's try that again. See how easy it is to make a mistake on these. So if I just multiply that by 1.47 times 10 to the minus 8 again, I should get the correct answer. Yes, so 3.73 times 10 to the minus 23 centimeters cubed. Alright, so as you can see, very simple to sort of lose track of what's happening and make a mistake. So then we are asked to do the density. So I'm going to do the same thing again here. Right. So it doesn't matter which one you choose because it's completely symmetric. So the same process is going to give you either the boron or the nitrogen. So let's choose one of these top ones. Okay. Now, if you think about it, being on the top here, I've already sort of cut through the atom. Half. Okay, so one half is above, one half is below, and then I need to work out what fraction is inside. Now, if you're on a hexagon, okay, so if this is a hexagon and you're next to two other hexagons, this angle here is 120 degrees. So if I've got this circle here, what fraction of this circle is inside this hexagon? Obviously 1/3. So because I'm cutting it through the middle, I get a half, and then how much of that half is inside the cell? 1/3. So 1/6 of this is inside the cell. Okay, so the logic again, if I just think about how much of the atom is inside the hexagon, I get 1/3, but then I cut it in half again because a half is above and half is below. All right, so I've got 1, 2, 3, 4, 5, 6. So I'm going to have 6 times 1/3. Okay, and then these ones here, these ones are not cut in half. So there's 1/3 of each of these inside. So plus 3 times 1/3. Oh no, I'm getting confused all over the place here. So sorry if this becomes a little bit more tricky to follow because of all the mistakes I keep making. So let's go back and have another look. Let me write it on. So this one here, that's 1/6 is inside, and this one here, that's 1/3 is inside. Okay, so how many have I got? I've got 1, 2, 3, 4, 5, 6. So 6 with 1/6. And then 3 with 1/3. Okay, that's fine. So 6 times 1/6 is 1, and 3 times 1/3 is also 1. So that gives me 2. And then it's the same for, it's the same, exactly same logic for the other one. Okay, sorry if that was a bit confusing. If you just pause in and go back, despite my mistake, it should still be able to, you should still be able to work out what I'm saying. And then it's the exact same calculation that we did before, except now, instead of 4 of each one, I've just got 2 of each one. So in fact, the mass is just going to be half of this. So if you want, you can do the whole thing. You do 2 times that, gives you the new value, divided by Avogadro's constant. All I'm going to do though is to work out my new mass, I'm going to divide that by 2. So I'm going to do 1.65 times 10 to the minus 22, divided by 2, gives me 8.25 times 10 to the 23. So I know my new mass, let's just go density. My new mass is 8.25 times 10 to the minus 23, and I'm going to divide that by the volume that I just worked out, 3.73 times 10 to the minus 23. So divide that by 3.73 times 10 to the minus 23, gives me 2.21 grams. 2.21 grams. Again, it's the right sort of magnitude of value that we would want. Sometimes there'll be something in the question that might tell you that the density is slightly, grams per centimetre cubed, that would give you a clue as to, because obviously now we've worked out that this is slightly lower density than this one, but I don't think there is anything in here that tells you. No, it just says that it changes. Okay, fine. And then, final. Calculate the number of boron and the number of nitrogen in WBN, this one here. Okay. So, corner. I've got 1, 2, 3, 4, 5, 6, 7, 8. So this is for boron, is 8 times 1 over 8. And then this one is in the middle. Okay, because you can see these nitrogens are on the edges, and it's sort of going in, coming in, going in. All right, so that gives me 2, and then you can just stop there because you can just go boron 2, nitrogen 2. You don't remember. You don't even once you've worked out one, you don't need to work out the other one because you know the empirical formula is Bn, so it has to be equal. But if you wanted to, you could work it out. Okay, and you'll see that I've got edge 1, edge 2, edge 3, edge 4. So that's 4 times 1 over 4. And then this one here, it's difficult to see with the colours here, but it is going in. So it's that, and then the fine nitrogen is completely inside the cell. Okay, so big question, lots of marks available, goes over, we went from electronegativity all the way through to unit cells. Lots of fun.